Okay, this is chapter 5, section 5, equilibrium of a rigid body in 3 dimensions. And that's the second time that we are doing the same problems, but now we will use the vector method with a table. So first we need to go back on our free body diagrams and add forces. We know that the forces that is applied is 80 pounds, and it's given. And the forces that we don't know are the tension in the cable TC, the two translation on X, and the two translation that are prevented, so the two forces and the two moments, A on Z and A on X. I don't try to guess the direction of those forces in 3D. In 3D, I just put everything positive. So X going in the same direction than the axis X, Z going in the same direction than the axis Z, and X rotations that is plus. Oops, where did I get my green, my golden? So in the positive directions and AZ in the positive direction. So when you step on the axis X and you look at the point A, you should rotate in the counterclockwise directions. And you step on Z and you look at A, you should rotate in the counterclockwise direction, in the positive direction. Okay, so we will use our sum of the forces as a vector, it's equal to 0, and sum of the moment, it's equal to 0. So for the force, what we need is the sum of Fx on I hat plus the sum of Fy on J hat plus the sum of the Fz on K hat is equal to 0. Okay? For the moment, that's the same thing. We need the sum of the moment on X, etc. But how do we find the moment in 3D? The moment about the point, so we will use the point A. About the point A, it's equal to what? It's equal to R from A to the force, cross product of the force. Okay, so the method I will show you, what you need to do is to determine which point you will apply the equation of moment. After that, you need to find all the points where there is a force applied on it. You need to find all the vector position, all the force, and you need to do the cross product of the vector position times the force to find the moment. And we will add all the moment together. Okay, so let me rewrite the moment about A. It's equal to R from A to the force, cross product of the force. And my advice is to do a table. So I will do the table. I will show you what I put in my table. Oops. So the first column is for the point I will consider. The second column is for R from the moment. So here it will be from A to the point that I consider. It will be a vector. It's a vector position. After that, we will have the force, and it will be also a vector. And the last one will be the moment. And the moment is equal to R, so A to the point, cross the force, cross the force F. And the moment is also a vector. Most of the time, the moment is a little bit longer to write, so I make a bigger box. Okay, so the point that I will consider. The first point will be, so everywhere you have a force, you need to write the point. So we will need to write the point A, the point B, and the point D. Okay? If you have more force, more points, write more. So A, B, and point D. Okay, you clean that. I wish I have a ruler like this when I am in the classroom on a whiteboard. That's so convenient. Okay, so this one will be R from A to A. Okay, so A, this point A, is the point of your moment. Because we have a lot of unknown at the point A, we will use the moment about A. Okay? So RAA will be equal to 0. Okay, so for the point A is 0. The force at A, what are the force? There is two components on X. So there is AX on I at and plus AZ on K at. Okay, and your moment is what? Is 0 cross AX I at plus AZ K at. So it's equal to 0. No moment created by the point A because we are doing the moment about the point A. But don't forget that we have the moment created by the reaction. So we have M AX on I at and plus M A Z on K at. Okay, so we need to consider them. Okay, there is no moment created by any distance for the force, but there is some moments, like internal moments inside the bearing. Point B, let's do point B. So this one. So what we need is RA, B, the vector position from the point to the force. So that's this distance, that is equal to minus 3 I at, and on J at, don't see anything there, plus 6 J at. Okay. The force at C is TC on K at. So make sure that you are in the right direction. Now the moment is minus 3 I at plus 6 J at cross TC K at. Remember, the moment is the vector position cross the force. There is an unknown there, so it's not very convenient using the cross product program in the calculator. So we need to do it by hand. So remember, I, J, K plus, and if we do I, K, J, I minus. So minus 3 I hat cross TC K at. It will give us J at and I cross K. So I cross K is minus J. So minus 3 minus, so it's give us 3 TC on J at. Okay, you need to practice the cross product. Okay, and 6 J at cross TC K at. So J cross K is plus I hat. So plus, and 6 J at, 6 times TC, so 6 TC. And it's plus. So that the moment created by the force. Oh, why I did. Sorry, that's the point D. What? That's the point B. That's the point B. That's the point B. Sorry. I call this TC, but I should call it TB. Right? I don't know what. Yeah, okay. I should call it, you know what? I should call it TBC. So now we're good. So that's TBC. That's so hard to just make a little eraser. Okay, and at D. So D is this point. What do we have? So D, we need our A D, the vector position going from the point to the force. And it's equal to minus 1.5 I at and plus 6 J at. Oops, let me make it a little bit bigger for you. And the force is minus 80 pounds going down on K at, aligned with Z. So the moment there is minus 1.5 I at plus 6 J at cross minus 80 K at. Okay, so let's do this. I cross k minus again, minus 80 times 1.5 on j at, and 6, so j cross k plus I, so I, and 6 times 80 with a minus, so minus 480 I at. And this one, so let's write it in the right direction. So it's minus 80 I at, and minus 80 times 1.5 minus 120 j at. Okay, let's square that because we have a lot of information. So we have the forces, and we have the moment. Okay, so if we write the equation sum, and I will make it, let's check, sum of the forces is equal to 0. What do we write there? We write that AX I at plus AZ K at plus TC K at minus 80 K at, it's equal to 0. And if you write sum of the moment about A, it's equal to 0. Which equation do we have? We have MAX I at plus MAZ K at plus 6TC I at plus 3TC J at minus 480 I at minus 120 J at is equal to 0. Okay, that's the two vector equation that we have. Here we go. If we use fx, we end up with ax, it's equal to 0. If we use f, and now we have fy is 0 equals 0, so we don't do it. And if we have fz, it will be az plus tc minus 80, it's equal to 0. So let's write az plus tc, it's equal to 80. Okay, we have two unknowns we cannot solve. Let's go on the moment equation. So on the moment on x, we have MAX, the coupled reaction at the bearing A. So I plus 6TC on I minus 480 is equal to 0. So we can write MAX plus 6TC is equal to 480. My, what do we have on Y? We have 3TC minus 120, it's equal to 0. So TC is equal to 180 divided by 3, so it's 40 pounds. Woohoo, first. So second answer, we have this one, that was the final answer. This one, final answer. And MZ, so we have MAZ on K, let's go around, it's equal to 0. So one more answer. Now that we know TC, we can go to this one. So let's go to this one, second step. So we have AZ plus 40 is equal to 80. So AZ is equal to 40. Okay, and last steps. Now we can go to, what's happened? We can go now to this one. So MAX it's equal to 480 minus 6 times TC, that is 40. How much is that? 240? Yes, 240. And everything is pounds. Don't write the pound there. Pounds. And that's the last answer. MAX is equal to 240 pounds. So we solve for our 1, 2, 3, 4, 4, 5 unknown. Here we go. Okay, so this method was longer for this example. Definitively. Look, oops, I have the other method there. It was longer. That's why I use this whiteboard, because I can extend my space as much as I want on the whiteboard where I write. It was longer, but in some cases, that's the only way we can solve for 3D problem. Not the only way, but the easiest way that we can solve for. So what we have to remember is in this table, what we do is we do which color do I use for view? Let's put a little bit of color. Oops. What we did. Point first. R, vector position, vector force, and vector moment that is equal to R plus F. R plus F. Okay? And in this table, every point you should consider is every point where there is a force on it, given or unknown, and R is going from the point where you do the moment to the point. Yeah. Usually you use the point that you use to do your moment is at least one that where there's a force, and the best most of the time is to use the point where there's the more unknown. So that's it for this example with this second method. See you in the next video. Bye bye.